Hello everybody, welcome to another video of Calculus 1. In this video we're going to be practicing derivation problems. More specifically, we're going to be using limits as h approaches 0. I want you guys to be more used with limit first, then we'll be using derivation rules. So in the second part, what we're going to see is there's a rate of change. I'm gonna go in more details with the rate of change. This is more applicable to physics and other subjects such as chemistry. Okay, so let's get started. The first question I'm gonna ask is, let's see, yeah, let's look at, yeah, okay, y equal to 4x minus 3x to the power of 2, and I want to find its tangent. Okay, let me just write the question first. Find the tangent line at y equals 4x plus 3x to the power of 2 at point 2 comma minus 4. All right, so let's do this. Okay, first I'm gonna put my derivation equation, right, my derivation limits, or whatever you can call it, for my derivation. Okay, good. All right, so now I just have to replace x plus h in my function. So let's replace this. It's going to be 4 parentheses h plus x plus h here, plus 3 parentheses x plus h to the power of 2. Then I'm going to do minus 4 minus 3 to the power of 2, because just for you guys, this 4x plus 3x to the power of 2 is a parenthesis, so with a negative in front, I'm gonna distribute my negative. Keep it just for you guys. So that's why I have directly opened the bracket right here. All right. So you guys should be more careful with those kind of questions, because it's very easy to make this kind of mistake. And this is how you lose point in easy question. Right, divided by h. Let's not forget that. Okay. So let's try to apply what we have learned in limits. What we have learned in limits is that I can just expand it, conjugate it, or factorize it for now. This is what we have learned so far. So I can simply expand expand everything in my numerator. All right, so let's do that. Okay, so I have already expand my 4 times x plus h. Okay, then I'm going to expand my x plus h to the power of 2. I'm going to get something like this. That's 3x divided by h. Then I'm gonna, did I miss something? Yes, I missed something. I forgot my 4x. Let's expand it again. This time I'm going to expand my 3 in, I'm going to distribute my 3 in my parentheses. It's 2 minus 4x minus 3x to the power of 2. I don't have any space. Right, now let's write it again here. Here I can cancel out 4x and 3x to the power of 2. Okay, so I'm left with 4h, 4h, yep, 4h plus 6xh plus 3h to the power of 2 divided by h. Yep. Alright, so let's just check if I made a mistake. Nope, everything is good. Now let's factorize our h. Yeah, factorize our h is gonna get 4 here plus 6x plus 3h, and I can cancel out h here, and I'm left with, if I plug in my h in my, if I plug in my 0 in my function, I'll be left with 4 plus 6x. And if you guys followed my last video, we learned that if f of x equal to x to the power of n, f prime of x, in other words, the derivation of my x of x to the power of n is equal to n times x to the power of n minus 1. Let's apply that here. Okay, so 4, let's take, just try to take it here. This is my f of x. If I take my f prime of x, my derivation, it's going to be 4 times 1 times x to the power of 1 minus 1 plus 3 times 6 times x to the power of 2 minus 1. It's going to be left with 4. This is going to be 1 here plus see, I went a bit too fast right here. Plus 3 times 2, I'm left with 6 to the power of 6 times x. Okay, so this is the same answer right here. Just like I have confirmed that I've done the right thing. Right. Okay, so this is how you use this is how you derive with limits. Okay. I'm gonna give you a second one. This time it's gonna be y equal I'm using my word, square root of x. So let's plug in this is h. Let's just derive it with my limit, right? At this point, you guys should be able to follow me. I got there. I just plug in h. I just plug in h plus x plus h and x inside of my function, inside of my equation. I mean, right. So here, what we can do right here, if you just h plus 0, I can't simplify it. What I can do, if I can't simplify, I can't factorize, I can conjugate, right? So let's conjugate. So here instead it's gonna be plus this and multiply by my denominator as well. Right? So let's find my numerator. It's gonna be x plus h plus x plus h minus x, right, divided by h. Yeah, and same here. Oops. Okay, at this point you guys should be able to follow me, right? So just conjugate it and multiply it and simplify it. All right, so I'm just gonna write this. Wait, Give me a sec, my hand are wet. Right. Just gonna write this again. Right. At this point, this equation should be trivial for you guys. Right. So now let's continue. My x and my x can cancel out, so I'm gonna be left with h on top. So let me just erase that part. So I'll be left h on top, h on the bottom. Yikes, it's kind of whack. Right, so cancel out my h. Right, if now just right here. Okay, so it's just gonna be square root of x. Let me just get more space. Square root of x plus h plus square root of x. Yeah, right. Now if I plug in my h, if I plug in my 0 here, my h is just gonna be 0 here. And I'll be left with square root of x plus square root of x. I'll be left with 1 over 2x. Yep. Now, let me just see if I made a trivial mistake here. Doesn't seem like it. So let's see if I got the right answer. Right. I need more space. It's not enough space. Let's open up a new tab. So what we got for our limit is just write taken here. Okay, so if I remember clearly, as limit h plus 0 for x plus h minus square root of x divided by h is giving us 2 times 1 over 2 times square root of x. Now our equation was square root of x here, so let's derive it using my derivation law. Okay, so my x prime of x is gonna be equal to, if I remember clearly, so it's here I'm gonna put 1 over 2, right? And so my 1 over 2 is gonna go in front. Then it's gonna be multiplied times 1 over 2 minus, no, it's gonna be 1. Yeah, 1 over 2 minus 1. Okay, and this will give us x minus 1 over 2 minus 1 over 2 minus 1 over 2, and this will give us, we can just rewrite it as x 1 over 2 on the bottom. So I can just rewrite it as 2 square root of x. And yes, we got the same answer. Because some of you don't need to write all of this, right? Oops. You guys don't need to write all of this. Not need. No need. But I'm just doing this for you guys to just keep up with me, to know how I got to this answer. And for those who find this a bit too long, now we can just skip it, you know. Right. So now that we are more used with derivations, well, I'm gonna let's look at a rate of change, right? So let's try it. Rate of change. All right. So, what is the rate of change? Well, my rate of change, I'm just gonna write it here. Uh, rate of change is the small, smallest, smallest decimal, small, I don't know, the small change on y and small decimal, how do I, yeah, small change and smallest, I'm just gonna write, right. Yeah, so I realize now my rate of change is the infinite infinitesimal infinite is it the infinitesimal, yeah, infinitesimal change, just need to write it here, infinitesimal change in y divided by the infinitesimal change in x. And this infinitesimal change, I had problem looking, so I have lost words for this, that's why I was struggling trying to find a definition for this. But yeah, there are, I have to remember some vocabulary. Yeah, so this is an infinitesimal change in x. So what I mean infinitesimal is, you guys know that x, y, you know that delta y divided by delta x give us a slope, right? It's the same thing as y2 divided 1 minus y1 equal to x2 divided minus x1, right? This is a slope function. Well, my rate of change is telling me that if, right, let's write a function right here. This is my x, this is my y, and this is a linear function, and this is my delta, this is my alpha, this is my delta y, this is my delta x. And what is this definition telling me? It's telling me the infinitesimal change in y. So my y is getting smaller and divided by infinitesimal change in x, and my x is getting smaller. So as you approximate, as you make xy, the interval of xy smaller. For example, this is 8 and this is, wait, if this is 8 and this is 2, my delta y will be 6. But let's take it another step. If this is 7 and this is, I don't know, 3, my delta y2 will be 4. So the concept of this means that as delta y is getting smaller, as delta x, okay, as delta x is getting smaller, delta y is getting smaller as well. So let's write it. Let's write this definition as delta x gets smaller, delta y gets smaller as well. Thus, if you want to find the most accurate slope in a curve, dy will dy and dx, the alpha delta y and delta x will delta x and delta y and delta x will get infinitely smaller, right? So this is why instead of writing alpha delta y divided by delta x for the slope, we're gonna be writing it dy divided by dx. This is called the rate of change, right? So let's show you guys an example of that. So let's take a curve, for example, and this is my P and this is my Q, let's say. And if I want to find my tangent line from P to Q, this is going to be my tangent line, right? Well, you see my delta y, and this is my delta y, that's my delta x. It's quite far, right? But if I take Q close enough to P, my delta y2 is small, such a way that let's write it somewhere else. In such a way that it gets so small that it is just 1 point. This is the concept of infinitesimal change in delta y and infinitesimal change in delta x. Right? This is dy dx. And let's take a linear function again. I want to just take another page instead. So if I want to be writing this in this linear function, y equal to mx plus b is going to be y equal to y equal to delta y divided by delta x times x plus b. So this is the rate of change. Or if you want to write like this. Actually, no, let's leave it out here. So this is the rate of change is what we're going to be looking in this video. Let's erase everything and let's give you guys an example. So here, before I get do another question, I'm gonna be giving you a fact. So the I'm gonna let's start with the question first. Okay, this is I think you guys are gonna love this question. Right, so this is t, and this is distance, so x, right? Julian plus s, let's call it distance. My s represents my distance, and I have a first linear, and I have like a sort of a curve of a parabola. Okay. All right, so I'm just gonna write my velocity. You guys just need to remember this. My velocity equal to my rate of change. Rate of change in terms of t. So it's basically, let's write this. In physics, you guys, if you're taking physics courses, you know that delta y over delta t, in our case it will be delta s right here. Delta s over delta t is our velocity, right? Because meter per second, meter per second, meter represents distance, second represents time. So the unit kind of give us away, right? So this is our equation for the velocity. So if I want a infinitesimal change, it's going to be a ds over dt. All right, so let's continue. I'm just going to give the equation, my equation for my linear function. So I'm just going to write, it's going to be a and b. Okay, and my a is, let's write it here. So let's just write y equal to, let's just think of, yeah, 50 over 7t. And for my b, my function is equal to 25 over 49 t to the power of 2. So my first question is, at what time is the distance the greatest? All right, you guys can practice this on your own, but yeah, let's go. All right, this one, if I want to do this, I forgot to continue the question. At what time is the distance greatest between A and B? Now you can try it. Now you can try this on your own. Right? You can pause the video and try this on your own. Okay. So what I'm gonna do is take my distance is basically 50. Wait. Sorry. So it's basically 50 over 7 t minus 25 over 49 t to the power of 2. So this is my distance, right? So if you guys look at this, if you guys look at my distance right here, at 0, the distance is equal to 0. So just gonna write this note here. At x equal to 0, and let's just give this x equal to 14 right here. I say 14, but in reality it doesn't matter. Right. And you guys can also do like comparison to find my point right here when they meet. And so instead I'm just giving you the where they meet, right? At 14 as no, this is at x equal like as t at t equal to 0 and at t equal to 14. My difference my uh the difference between a and b is equal to 0, right? Then yeah. So this is basically a minus b right here. This is my distance a minus b. So if I put my graph right here, this is 0 and this is 14. And if I just look at this, at the beginning, my distance is increasing, right? You can clearly see that my distance is increasing between A and B. But then at what point it starts to decrease? Does that give you an idea? That's what it does to me, right? We get a sort of a parabola. This is my distance right here. My D, my difference in my distance, right? So difference between A and B. This is time. So this is a graph we get, and maybe like Kavish, we're still confused. Well, if you guys want to know, this is my maximum right here. So if I take my tangent line over the maximum point, right, the maximum of my function right here, I'm gonna get dy over dx equal to 0, right? It's like a linear function, like a line right here. And if you want to find the slope here, my slope is going to equal to 0. It's the same thing. When at d max dy over dt, dy over dt equal to 0. Here will be not dy, it would be dt, dd over dt. dd over dt equal to 0. Okay, this is something that you must know, right? This is how we find the minimum and the maximum. As we're gonna go in more details in this at the end of the year when we're gonna try to find. I'm gonna try to graph a function, and this is gonna be the best part of calculus 1. You're gonna see, right? So let's derive this equation, right? dt over dd over dt should equal to 0. So let's derive this. Well, if I derive my t is going to be equal to 1. If I derive my t, my constant is going to be the same. And if I derive 25 divided by 49, it's going to be 2 times 25 divided by 49 times t to the power of 2 minus 1, giving me 1. And this is going to be 0, right? Because when d is maximum, my dt over dt is going to be equal to 0. So I want this to equal to 0. Minus 50 over 59, 49 equal to 0. This is t. 50 over 7 equal to 50 over 49t. I want to isolate. So this is gonna cancel out with 50 here, right? And here is going to be 49 over 7t, and you can just rewrite it as 7. All right, so I'm just going to do a recap. right? Um, the when your the derivation can be written as dy over dx. This is my derivation. So it's basically limit as h approaches to 0 f of x plus h minus f of x divided by h. Same thing. Instead, I'm trying to explore the connection between the rate of change and the derivation. So if you want to find the slope of any function, you have to derive it, right? So this is how calculus is. Any rate of change. So anything counted out like velocity could be how many bananas can you make per hour. How many bananas can you make per hour is the rate of change. So if you want to find the velocity, if you want to find the rate of change of how many bananas you can make per hour, you have to derive the equation of your function. So I'm just going to give you an example. Later on, we're gonna explore this more. Right now, this is kind of a demo. For example, if I have like a water right here, and my water is rising, you're gonna have like a milliliters per second, and this is the rate of change. This is like dv over I don't know, dt, right? This is the rate of change, and this is I want you guys to be familiar with this, right? Uh, because you can get problem like this, and you're gonna be using this in physics if you get to college level. You're gonna use this a ton of time, and trust me, you're never gonna get bored with calculus. And before we leave, I want to present you guys one of my favorite questions. Right? So this type of question, uh, right? This type of question is on your book in chapter 2.7 in James Jodwell's calculus book. So instead, I'm changing a bit of stuff. So I'm writing 50 meters per second, and I'm going to give you this. This is my velocity. Just going a baseball bat has an initial velocity of 50 meters per second. And the height presents y, which its function is y equal to 9.8 t divided by 2 plus 50 t. Find the velocity at t equal to 2. All right. So what should we do? The first thing you guys should do is try to graph it first, right? So if I try to graph it, I'm gonna have something like this, something like this. So this kind of function is like a parabola, and it wants me to find the velocity at t equal to 2. Well, remember my rate of change equal my derivation, right? So, oops. So if I take this, if I take my tangent line, this is my rate of change. So we want to find the slope of my tangent line, right? So how should we do this? Well, this is my f of x. Oh god. Yeah, this is my f of x. And this is my f prime of x. Right, so let's derive our function. If I derive my function, I'm going to have dy over dt equal to 9.8 plus 50. 9.8t plus 50. Right? I hope I don't have to explain to you guys. My 2 goes over there, which cancel out my 2 in my denominator. And 2 minus 1 equal to 1, so t to the power of 1 equal to t. And t, derive your t here is going to equal to 1. So this is your derivation. This is your rate of change. In other words, this is your velocity equation. Alright, so now he's just asking you at t equal to 2. So let's just plug in t equal to 2. So here, let me just calculate it real quick. It's going to give us 16, here will be 19.6. That's right, 19.6. 8, yep, plus 50 give us 69.6. All right, I'll have to calculate. I don't have my calculator with me right now, so I'm just doing everything in my head. All right. So this is our velocity at t equal to 2. All right. And this kind of makes sense, you know. This is like a linear, and this is a parabola. Right? So if you derive x equal to 2, it's going to give you x, 2x, right? It's going to give you 2x. And yeah, x is linear. So kind of makes sense, right? So this is all for this video, and I hope you guys are following me. If you have any question, write down in the comment down below. And what we're gonna do in the next video, we're gonna be learning the chain rule. At first I was planning to teach you the chain rule before this video, but I just want you guys to understand how derivation are used. Most importantly, the rate of change represents the slope, right? So to recap, the infinitesimal change of y divided by the infinitesimal change of x is going to give you the slope, the most accurate slope in any function. So this is why we are going to use derivations, and this is the application for derivation. Certainly in physics. In physics, you're going to learn how to use derivations um, to find the velocity. Yeah. So this is often used in university. This is like the ABCD in engineering. And I hope you guys understand, and I hope you have a great day.